Hi, my name is Marcus and I'm working at DYNAmore Nordic, and today I'm going to show you how to set up a 2D FSI simulation in LS-DYNA. First we're going to talk a little bit about the ICFD solver, which is the CFD solver in LS-DYNA. Then I will give a brief introduction to the fluid model, and then I will go through how to set up the structure model. And after that we're going to define the FSI connection and do one small modification to the fluid model. And then I will go through how to post-process the results. So the ICFD solver in LS-DYNA is an implicit solver, and it has an automatic volume measure. So as a user, you provide the surface mesh, and then the solver will generate the volume mesh based on the surface mesh. But it's also possible to define your own volume mesh as long as you use tetra elements. The fluid model is the same as in the previous webinar, and if you missed that presentation, it's available at our website dynamore.se and on the YouTube channel LS-DYNA Corporate Tutorial and Content. And I will give a brief repetition of the boundary conditions. The inlet has a prescribed velocity of 1, and the outlet has a 0 pressure condition, and the main boundaries has a free slip condition, and the cylinder has a no slip condition. Now over to the structural model, which is shown here in the picture. It has a radius of 0.25 and a x-coordinate of 4 and a y-coordinate of 5 for the center of the circle, which is the same as for the fluid circle. So the boundaries of the structural and the boundaries of the fluid will be placed at the same location. And the material that we're going to use is matte rigid, since we're only going to look on the vertical displacement of the structure. And the Young's modulus is set to 200 times 10 to the power of 9, and the Poisson's ratio is set to 0.3, and the density is set to 1.2. And if you remember the fluid case, we set the density to 1, so the fluid and the structure has a similar density. And for the boundary conditions, we will constrain all movements except the vertical displacement of the structure. And to generate the mesh, you can use LS Prepost, and you click on Mesh and Shape Mesh to open the shape measure. Then select the entity to circle shell and enter the radius 0.25. Set the density to a value between 30 and 40, and the radius in to 0 and the density into 0, and put the angle to 360 to get the whole circle. And then enter the center position to 4, 5, 0. And set the normal to in the Z direction by entering 0, 0, 1. And then press create. And if you don't see the model, press Auto Center or Ctrl A. And if you're satisfied with the result, press accept. And then save the mesh as mesh_struct.k, for example. And I mentioned before that the structural and fluid mesh do not have to be the same. And for the FSI criterion to work, the distance d here in the picture must be lower than 0.25 times the minimum element size between the fluid and the solid. And the displacement will be interpolated between the fluid and the solid, and also the loads. But if you use a matching mesh, no interpolation will occur. And the good thing with this is that it opens up for a good collaboration between the structural and the CFD group. So the structure group can create the mesh of the structure, and the CFD can mesh the fluid. And then we can connect the two simulation and do a FSI simulation. And in this example, the mesh looks like this. Here you have the structural element, and the yellow dots here are the fluid nodes. So here you have one element side of the fluid mesh. So as you can see, it's quite a big difference. Now we're going to define the structure problem, and before we move on to the FSI keywords and the FSI coupling. So open a LS prepost window and include the previously created mesh_struct.k file, and then save the model as struct.k, for example. And then reopen the model in LS prepost to view the mesh. And the first keyword that we're going to define is the material keyword. So click on model and then keyword and go to map and locate the 020 rigid material. And enter a density of 1.2 and Young's modulus of 200 times 10 to the power of 9. And Poisson's ratio of 0.3, and change the CMO parameter to 1, which means that we will constrain the body here since it's a rigid body, and then enter 6 in con 1 and 7 in con 2. This means that all displacements are constrained except the vertical displacements. And then press accept and done. The next keyword is the section shell keyword, which control the element formulation. So in this case we're going to use element formulation 12. So enter 12 under L form here and keep the rest as default. This element is a plane stress element formulation, so only used in 2D. And then press accept and done. Now we can associate these keywords with the part keyword. So locate the part keyword and open it, and select the previously created section ID and the material ID. And check that you are in the right subsystem here, and if not, press setting and select the current file. And then press accept and done. Since we're going to use a strong FSI coupling, the implicit structural solver must be used, and to activate it, use control implicit general, and remember to set the im flag to 1, and then choose a time step, and remember to use a higher time step than the fluid. So in this case we can set 0.1, since we're later on going to set the fluid time step to 0.05. And the solver will use the lowest time step between the structure and the fluid if a strong coupling is used. And keep the rest of the parameters as default and press accept and done. To control which implicit solver to use the keyword control implicit solution. And from LS-DYNA version R9, the new default nonlinear solver is number 12, and that is the solver that is recommended to use as well. So if you haven't the number 12 selected here on nsolve, select it and then use the following parameters, which is the default ones. And the recommended change that we often give to customers is to set the absolute value to 1 times 10 to the power of -20, and then press accept and done. And to activate the dynamics, use control implicit dynamics, and remember to set the IMAS parameter to 1 to activate it, and enter gamma value of 0.6 and a beta value of 0.38. This will give you some numerical damping, and if you want an undamped system, use gamma 0.5 and beta 0.25, which is the default values. And the last control keyword that we're going to use is control termination, which control the end time of the simulation for the structural part. So set it to 100, which is the same as for the fluid. That was all the necessary structural keywords. So now save the model and open a new LS prepost window and include the fluid and structural model. And then save the model as main_fsi.k or another name if you want. And now it's time to define the FSI connection. To activate the FSI, only 2 keywords are necessary. And we're going to start with the ICFD boundary FSI keyword. And open it in the keyword manager and then select part ID 4 and press insert and accept and done. And the next keyword is the control card for FSI coupling, ICFD control FSI, and locate it in the keyword manager and use the default values, which means that a two-way coupling will be used. It's the OVC parameter here that controls the coupling direction. Then press accept and done. No modifications to the fluid deck are needed, but to save computational time we will increase the time step. So locate the keyword ICFD control time and then change the DT parameter to 0.05. And if you use the fluid deck from dynaexamples.com, it uses parameters So then you have to change the parameter called dt_fluid and set it to 0.05. Another option is to scale the CFL number, which means that the time step will be scaled with a factor. And remember that if you use a too high time step, you will get inaccurate results. And to output the results, we're going to use a database binary dt_plot. And you probably already have it in either the structural case or the fluid model. But if you don't have it, locate it in the keyword manager and enter a dt of 1, which means that we will get 100 result states since the end time was 100. And some ICFD database keywords that are useful are the ICFD database drag that outputs the forces on a given boundary. In this case, use part ID number 4. And then we also have the ICFD database time step, which outputs the taken time step and the CFL time steps. And you probably already have these defined in the structural or in the fluid model. To run the model, you have to use a double precision version of LS-DYNA, since the ICFD solver do not exist in the single precision version. And I recommend to use a version of R9.0.1 or higher. And for Windows, I recommend to use the program LS-run that can be downloaded for free at our FTP site. And on Linux, the starting command will look different for each setup. And here is our command line, and we're using a script to start the MPP simulation. For more information, check the manual. And you could also use LS-run on a Linux if you want. And this model takes 20 minutes on 2 CPUs. And to post-process the results, open the dt_plot file in ls-prepost. And when you're performing a FSI simulation, you will get one structural group and then a fluid group for the surface part and one for the volume part. And in this case, we are in 2D, so you get a shell for the volume. And if you click on the structural part, you can go down to the display options and select a structural property that you want to display on the structure. And it's also possible if you right click on the structure to add some functions on the structural part. But in this case it's not so useful since the material is rigid and no deformation or stresses are present in the structural model. To plot the result from the ICFD database drag file, press MS and then MS ASCII, and then select the file that you want to load and press load and locate it in your output files. Then select the variable that you want to plot. And if you want to plot another variable in the same window, use p_add. And remember to include the ICFD database keywords before you start the simulation, otherwise you will not get any output. And for more post-processing information, sign up for the coming webinars and also check the presentation from the previous webinar. here is the result from the FSI simulation, and I have plotted the fluid velocity, and as you can see, the fluid starts to oscillate due to the vortex shredding. Here I have plotted the lift force from the ICFD database drag keyword, and I have plotted the pressure force as the red one and the viscous forces as the green one. So the green represents the friction forces on the structure, and the red one represents the pressure forces. That was all that I had for this webinar, and remember that the models can be downloaded at dynaexamples.com. So thank you for listening.